Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to perform principal component analysis for Likert scale items. Even before I proceed to demonstrate how to perform principal component analysis or PCA for Likert scale data, may I request you to subscribe to my channel, also like and share my videos. If you are a research scholar and you're not very sure how to handle a large Likert scale data set, this is a video that you should watch. Let's begin by asking a few simple questions. What is principal component analysis? Why use principal component analysis? What are the advantages and disadvantages of the principal component analysis? Then we will look at a practical example as to how you can go ahead, execute the PCA and learn to interpret the results coming out of PCA technique. Firstly, what is principal component analysis? Principal component analysis is a powerful statistical technique which is used to simplify and interpret complex data sets. It is a dimensionality reduction method that transforms a large set of correlated variables into a smaller set of uncorrelated variables called principal components. One question which people usually ask me is, why should we use PCA? There are 4 important reasons as to why we should use PCA. First, it simplifies complex data. That is, PCA reduces the number of variables, making it easier to visualize and understand the data. Number 2, PCA helps us identify patterns. PCA reveals hidden patterns and correlations between variables. Number 3, PCA reduces noise. PCA helps eliminate irrelevant or redundant data. Number 4, PCA helps improve model performance. PCA can improve the accuracy of predictive models by reducing multi-collinearity. You can use PCA as a standalone independent technique, or you can use PCA to generate the factor scores, and these factor scores can be used as input variables for linear regression. So both of these are possible. Let's now focus on what are the main advantages of PCA. First, dimensionality reduction. PCA reduces the number of variables, making data easier to analyze. Number 2, feature extraction. PCA identifies the most important features in the data. Number 3, noise reduction. PCA eliminates irrelevant data. Number 4, improved visualization. PCA simplifies data visualization. Let's now look at the disadvantages of using PCA. Like with any other technique, there are problems with an algorithm. PCA is no exception to this rule. There are 4 important disadvantages of using PCA. First would be loss of information. PCA discards some data, potentially losing important information. Number 2, PCA assumes linearity. This is a very important point. PCA assumes linearity. PCA assumes linear relationships between variables. However, if the data is nonlinear, PCA is not an appropriate technique. Number 3, PCA is sensitive to outliers. PCA can be affected by outliers or extreme values. Number 4, interpretational challenges. PCA results can be difficult to interpret, especially for non-technical audiences. With this background, let's now proceed to look at a sample data set using which we will be executing PCA in SPSS. For this video, I'll be using a sample data set which is called as the phonofilm data set. This is a data set about participants' preference towards deriving entertainment. That is, do you like to derive your entertainment by watching movies or by playing a particular sport, or are you a party animal? There could be any of these things. There are 21 Likert scale items. The first variable here is ID. The second variable that I have is attitudinal 1. This is the first Likert scale question that we would like to look at. As you can see, this question stands for I enjoy going to the cinema. Let's now focus on attitude 2, which stands for I like a wide range of choice in the video shop. What about attitude 3? Attitude 3 talks about my leisure activities are mainly out of home. These are the first 3 attitudinal questions. Like this, I have around 21 variables. As I scroll to the right side, you can see the last variable that I have is attitude 21. So I have got 21 Likert scale items. Participants have given a response towards each of these 21 items. As you can see here, the first person whose ID is 2 has given a rating of 3 for the first Likert scale item. He has again given a rating of 3 for the second Likert scale question, and for the third question, he has given a rating of 3. If you want the corresponding value labels against each and every question, let me go ahead and click on value labels icon. You can see here, it says neutral, neutral. For the third question, it says strongly disagree. Similar responses are given against each and every question. What is the sample size in this data? To check the sample size, let me go to the last record. It is 328. So with a sample of 328 and a column, my apologies, with a data set comprising 21 Likert scale items, I'd like to run a PCA. 21 is too many. I'd like to reduce the number of columns from 21 to fewer columns. How do we do this? To execute the PCA algorithm, what you need to do is go to the Analyze menu bar. Once I click on the Analyze menu bar, you can see there are a lot of options under this. Let me move to the option Dimension Reduction. Now, under the Dimension Reduction section, you have several options. Let me go ahead and select the first option, namely Factor Analysis. Let me hit the Factor button here. You can see this opens up a new dialog box, which is called as Factor Analysis dialog box. In the left-hand side, you can see all the variables that are present in the data set. What I'd like to do is I'd like to enter each of these 21 columns and move it into the variables box. So what I'm effectively telling PCA is to take these 21 columns and reduce it into a lower dimensional space. The word dimension here refers to columns. There are a couple of prerequisites that you need to go through. You can't use a statistical technique just like that. We have to see whether the data that we have is suitable for a technique like PCA. Now, there are 2 prerequisites that I'd like to check. For this, I'll be using the descriptives button at the top. Let me go ahead and select the descriptives button. you have the statistics section as well as the correlation matrix section. You can click on the correlation coefficients. And the second thing that you need to tick is Kmod and Bartlett's test of sphericity. Kmod and Bartlett's test is a very, very useful test. For those of you who are very new and are unfamiliar as to what is Kmod, Kmod is a statistical test named after three statisticians, Kaiser-Meyer-Olkin. This is a multivariate test of normality. The second test is Bartlett's test of sphericity. This is a test which checks whether there is sufficient correlation in the dataset. This becomes a prerequisite for performing PCA. Without these techniques, it is advisable that you do not perform PCA. With these selections, let me go ahead and hit the continue button. This is as far as descriptives is concerned. The second option that I'd like to select is what is called as extraction. Let me go ahead and select extraction. The method that I'll be using under extraction is principal components. If you click on the drop-down menu, you can see there are other options as well, like maximum likelihood, principal access factoring, so on and so forth. I'll go ahead and select principal components. There's a very interesting graph which is called as the scree plot. It is very, very important that we use the scree plot to decide the optimal number of components that we will be extracting. Now, let's look at the extraction method. There are two methods. One is based on the eigenvalue. Remember, eigenvalue is a measure of variance. The default option uses an eigenvalue which is greater than 1. There's another option which says fixed number of factors. If you're already sure or very, very clear that you need to extract X number of factors, let's say 3 or 4, you can go ahead and specify 3 here. I'm not very sure. So since this is an exploratory data analysis and not a confirmatory data analysis, I choose to allow the software to decide the optimal number of factors. Let me go ahead and hit the continue button. We are through with descriptives and extraction. Let me go ahead and select rotation. Under the rotation method, you can see there are 5 important methods. One is Varimax, then you have direct oblimin, Quantimax, Equimax, and Promax. I'm going to go ahead and select the Varimax rotation method. After selecting Varimax, let me go ahead and select the continue button. Now, let me select the option scores. In case you want to create new component scores, you can go ahead and save the new components. How do you do this? Make sure that you check the save as variables option. Let me hit the continue button. The last of the options that I have here is options. Let me go ahead and select options. You can see here missing values. This specifies how you treat the missing values. If you're not very sure, it's better to leave this at the default option. The next section is coefficient display format. I'm going to check this option, sorted by size, suppress small coefficients. Here, I'm going to specify a value of 0.3. In other datasets, you can choose a value of 0.6. 0.6 is a better number. However, for the purpose of this video, I am choosing a slightly conservative estimate of 0.3. We can always feel free to experiment with this number. This is only for better interpretation of the loadings. With these selections, let me hit the continue button. Now, we are all set to execute the PCA. With these selections, let me go ahead and proceed to click on the OK button. As you can see, this is the output window of SPSS. In the left-hand side, you can see the output of factor analysis. You can see here The first of the table is the correlation matrix. My first impression when I look at some of the numbers is that it is a good sign. It looks like I have sufficient correlation in the data. Typically, watch out for numbers which are greater than 0.6. If you have correlation values bigger than 0.6, it is a good sign, which means that your data is suitable for performing PCA. On the other hand, if you see weak correlation, you should not perform PCA. When I look at the correlation values here of 0.724, or let us say some other numbers like negative 0.736, here again I have negative 0.749. These are all relatively on the higher side, indicating that there is sufficient correlation. So PCA is a meaningful and a relevant technique for my data. However, there is a more easier way to check whether your data is suitable for PCA or not. There are two important tests which I mentioned earlier. Let's focus on the Kmod test. This is a small table, but very, very informative. And I'd like to draw your attention to a few numbers here. As you can see, SPSS displays Kaiser-Meyer-Olkin measure of sampling adequacy. It says it is 0.84. How do we interpret this? Let me just double click, right click and say, what is this? SPSS displays an explanation for Kaiser-Meyer-Olkin. It says this is a measure of sampling adequacy. It tests whether the partial correlations among the variables are small. Bartlett's test of sphericity tests whether the correlation matrix is an identity matrix, which would indicate that the factor model is inappropriate. For those of you who are struggling with the interpretation, let me just break this down in simpler language. Let's first focus on the Kmod test. What is the purpose of doing the Kmod test? In simple layman's language, Kmod test checks or evaluates the suitability of your data for PCA by looking at two important conditions. The first thing that it checks is multivariate normality, which is one of the assumptions of PCA. What do I mean by multivariate normality here? We are checking how well the data follows a multivariate normal distribution. The second thing that Kmod checks is sampling adequacy, whether the sample size is sufficient for PCA. If you have a data set with a very tiny sample size, it is better not to use PCA. If I have to give you a small rule of thumb to check whether the sample size meets the criteria or not, you can look at a simple condition which is called as acceptance criteria. What is this acceptance criteria? Kmod value should be 0.6 or higher, preferably above 0.7. You're always safe. If the Kmod value is 0.6 or higher, it means that it is good for PCA. In other words, there is adequate sampling and multivariate normality. Many times, the Kmod value may be between 0.5 and 0.6. What does this mean? If the Kmod value in the data set is between 0.5 and 0.6, it means that it is acceptable, but you should be cautious because this implies borderline sampling adequacy and normality. The third case is if your Kmod value is less than 0.5, you should be really worried because this clearly indicates that the data is not suitable for PCA. In other words, there is inadequate sampling and non-normality. In my case, I'm getting a sample size, my apologies, I'm getting a Kmod value of 0.840, which is clearly greater than 0.7, and therefore I pass the first test. So congratulations, the Kmod value is doing quite well. Let's now focus on the Bartlett test of sphericity. Here, SPSS reports the approximate chi-square value, degrees of freedom, and significance. We can directly look at the significance value here. What is the significance value here? It is 0.000. Even before I jump to the interpretation of 0.000, for those of you who are non-statisticians and you're wondering what is this Bartlett test, in simple language, using the Bartlett test, I'm checking if the variables are too random or uncorrelated. Now you may ask me what is the acceptance criteria under the Bartlett test. Watch out for a p-value. Ideally, your p-value should be less than 0.05. You heard me right? The p-value here should be less than 0.05. What if the p-value is less than 0.05? If the p-value is less than 0.05, we reject the null hypothesis, meaning that the variables are not too random and are suitable for PCA. What happens if the significance value is bigger than 0.05? It means that the data fails to reject. In fact, we fail to reject the null hypothesis, implying that the variables may be too random for PCA. What are we trying to measure? We are trying to measure whether the correlation matrix is an identity matrix or not. Here, in my case, clearly a value of 0.000 is less than 0.05. And therefore, the second test is also satisfied. So congratulations, I have the license to do PCA because both the Kmod test as well as the Bartlett test of sphericity has given me a green signal. In your case, if the Kmod measure is less than satisfactory or the Bartlett test is not up to the mark, it is better that you stop doing PCA and you have to go back, collect adequate data so that your sample size improves and think of more meaningful variables in the data set, and you have to rerun the analysis. There is no point looking at the further results if Kmod and Bartlett test fails. With this understanding, let's proceed to look at what is called as communalities. I'm going to give you a high-level interpretation of what is called as initial communalities and extraction communalities. This is reported for all the 21 variables. Now, again, if you are a non-statistician, you may be wondering, what do we mean by communalities? Communalities represent the proportion of variance in each original variable explained by the retained principal components. Communalities measure how well each variable is represented by the components. Communalities range from 0 to 1. 0 means no explanation and 1 means complete explanation. So this is how we can interpret the communalities. Now, let's proceed to another very important table, and this table is called as total variance explained. I know that there are a lot of details here, but for the purpose of clarity and simplicity, interpreting the first 4 columns, that is components, total eigenvalue, percentage of variance, and cumulative percentage would be sufficient. Now, those of you who are not very clear as to what is the meaning of eigenvalue. Eigenvalue represents the amount of variance explained by each principal component. It's a point which is worth repeating. Eigenvalues represent the amount of variance explained by each principal component. It measures the strength and importance of each component. Eigenvalues are usually listed in descending order, with the first component explaining the most variance. Here, when you look at the first when you look at the first column, you have the component number. Then you have the total eigenvalue. Watch out for these numbers. For the first component, the eigenvalue is 7.8. There is a criteria which is called as the K1 criteria proposed by the statistician Kaiser. It says if the eigenvalue is bigger than 1, select it, or else do not select it. 7.8 is clearly bigger than 1, so the first component is selected. Have a look at the second component. Here the eigenvalue is 4.13, again greater than 1, therefore I'm going to select it. The third component has an eigenvalue of 1.5, again greater than 1, so select it. Fourth component has an eigenvalue 1.07. This is a borderline case, therefore you can go ahead and select it because it is anyway greater than 1. Have a look at the fifth component. The eigenvalue is less than 1. It is 0.96, which is clearly less than 1, and therefore I will not be selecting the fifth component. The rest of the components have an eigenvalue which is clearly less than 1, and therefore we don't need to select component number 5 onwards. We can limit the analysis to the first 4 components. If I have to summarize the gist of PCA, you have to answer 2 important questions in PCA. How many components will you extract? The second question is, what do these components represent? I've answered the first question when I say how many components will I extract. Let's now look at the third column here, percentage of variance explained by each and every column. The first component explains the highest percentage of variance, which is 37. The second component explains 19. The third component explains 7% variance. The fourth component explains 5% variance. So the second column tells me individually what is the percentage of variance accounted for by each of the components. Let's look at the third component, which is cumulative percentage. What does this indicate? Now, to interpret the cumulative percentage, you need to pay attention to the earlier column, that is percentage of variance. So the first component accounted for 37, which is written as it is. Have a look at the second component, which accounts for 19. So 37 plus 19 would approximately be 57%. So the first 2 components account for 57% of the variance. Now, if you were to add the contribution of the third component, which is 7%, to that of 57, you'd get a total of 64%. Now, to this 64%, please add 5%. 64 plus 5 would be approximately 69 point something. So what I'm trying to say is the first 4 components explain 69.7% of the variance, or you can round off and say the first 4 components account for 70% of the variance, which is a big chunk. In the larger analysis, what does this mean? Remember, originally I had 21 variables. If the first 4 components are accounting for 70%, it automatically means that the remaining 17 components are explaining merely 30% of the variance. That is, their contribution is quite negligible, and therefore it is better to ignore these 17 components from the rest of the analysis. Now, let's proceed to look at the scree plot. This is the scree plot. Now, what exactly is a scree plot? Scree plot is a graphical representation of the eigenvalues of each principal component. You may ask me, why do we use the scree plot? Scree plot helps determine the optimal number of components to retain. The plot shows the eigenvalues on the y-axis. Have a look at the y-axis here. We have the eigenvalue, and in the x-axis, we have each of the components starting from 1 all the way up to 21. What should you look at? You should approximately look at a y-axis value of 1. Remember, Kaiser's criteria or K1 criteria clearly says that eigenvalue bigger than 1 needs to be looked at. Now, in statistics, there is a concept called as the elbow point or the knee point, which indicates whether the eigenvalues start to decline significantly, suggesting the optimal number of components. When I look at the first component in the x-axis, it has an eigenvalue of approximately 8, which is a good sign. Second component has an eigenvalue of approximately 4, which is again a good sign. The third component has an eigenvalue of approximately 1.8. The fourth has an eigenvalue of approximately 1.07. So the first four components are clearly greater than 1. But have a look at the fifth component. Its eigenvalue is less than 1. When you compare this with the y-axis value, it is less than 1. And therefore, we can say that from the fifth component onwards, since the eigenvalue declines or drops off, we can drop from the fifth component. We can just focus on the first four components which meets our criteria. So this is how we have to interpret the scree plot. Observe the elbow point or the knee point, which simply indicates where the eigenvalue starts to decline. I can see that from the fifth component onwards, this is a portion which is almost parallel to the x-axis. We don't need this portion because the contribution of each of these components is minimal, and therefore the optimal number of components in this analysis would be 4. Now let's proceed to look at the next option. We have what is called as component matrix, which is difficult to interpret. Therefore, let us proceed to look at the rotated component matrix. In the column, you have the 4 components. You can see here, this is component 1, component 2, component 3, and component 4. And along the row, you can see each and every original variable. For those of you who want me to explain rotated component matrix, what exactly is this rotated component matrix? It's a matrix displaying the loadings of each variable on the principal components after rotation. Rotation simplifies the interpretation of the components by grouping similar variables together. You can have a look at each of these numbers. These numbers can be interpreted as factor loading or component loading or correlation values. The matrix here shows the rotated component loadings, which represent the correlation between each variable and the component up above. You can see a few blank spaces here. There are numbers here, but the values are so small that I have decided to suppress these values. The question is, how do we interpret these component loadings? Now, and what are these component loadings? Now, component loadings represent the correlation between each variable and the principal component. The loadings here range from -1, which indicates perfect negative correlation, to +1, indicating perfect positive correlation. A loading value of close to 0 indicates little correlation between the variables and the component. Now, how do we interpret these numbers? Let me double click on the rotated component matrix. You can see here, the first component has a loading of 0.925 with the first variable. It has a negative loading on the second variable. Similarly, it has a loading of 0.853 with the third variable. The loading values decreases as you go down. So the first component, since it is loaded heavily with the first 3 variables, you can take a cutoff of 0.8. Many researchers take a cutoff here. You don't need to look at each and every value. You can take a cutoff of about 0.8 and focus on the first 3 or 4 variables which heavily influence component 1. The first item here is my leisure activities are mainly out of home, which means it represents a segment of the participants who derive their entertainment by going outside their home. So can I call them as social people? Possibly. The TV is always on in my household. I enjoy going to the cinema. Looks like he's a cinema buff. I rarely have time to sit down and watch TV. So since the first component represents people who derive their leisure by going out of home, I'm going to call the first component as social. So I have to connect it back to the original variables. The original variables speak about how do you derive your entertainment? What's your entertainment preference? So this represents a segment of people who derive their entertainment by going out, and therefore I'm going to call them as social. Now have a look at the second component. They're quite silent as far as the first few variables are concerned. This is a good sign. They do not have any loading with the first few variables. This is good because it would lead to a lot of confusion had there been a lot of loading with the first few variables. When I look at the second component, what is the highest number here? Let me scroll down. The highest number here seems to be 0.875. You can also look at some of the other numbers like 0.863, 0.845. Now, when you say 0.875, what does it indicate? Satellite and cable need more film selections. So he's asking for variety. Next, let's look at 0.863. I don't mind paying for more TV programs. Now, when you look at the third of the elements here again, it represents satellite and cable offer wider choices of films. He's looking for variety, and this component mainly loads with satellite and cable. So you can go ahead and call this as TV variety. Let's focus on the third component. What is the highest number here? I see a big number that is 0.866. This is with the variable. I often forget to return a rented video film. Now, whether he forgets or not, that is out of question. What I am interested in is the fact that he is renting a video film, and therefore I'm going to call him as a video fan. Let's look at the fourth component here. 0.357, 0.337, small numbers. The biggest number here is 0.776. I prefer films over weekly serials. The next is I get annoyed if the video I want is out. So let me go ahead and name this component as a film buff. So these are the four components that we have: social, TV variety, a person who seeks TV variety. You can also call this as satellite or cable film selection. The third is a video fan. The fourth one would be a film buff. Now you can experiment by rerunning the same analysis with 3 components. That's perfectly all right. Now, is this the end of factor analysis? Certainly not. We need to look at one more element. So I'm going to go back to the data set and show you how I have created the factor scores. So these are the 4 new columns. This is the second factor. I've got the third and the fourth factor scores. Now, what do these component scores represent? The component scores represent the coordinates of each data point in the new component space. These scores are calculated by multiplying the original data with the component loadings. Number 3, these scores help visualize and cluster the observations based on new components. For further analysis, you don't need to worry about the original set of variables. That is, from you had attitude 1 all the way up to attitude 21, which was pretty humongous. Working with 21 variables does not make sense. Now we have a smaller subset of variables, that is factor 1, factor 2, factor 3, and factor 4. Now, one very interesting point here is, let me go to the Analyze menu bar, Correlate, and choose Bivariate. This opens up a new dialog box. Let me scroll down. The last 3 variables, I'm going to move into the variables list. Let's look at the correlation among these components. Let me hit the OK button. You can have a look at the correlation matrix. Along the column, I have the factor scores. These are along the row as well. I've got factor scores. SPSS reports the Pearson's correlation significance value. What is the correlation for the first component with itself? It is 1. You can have a look at the diagonal elements. Since we are looking at the correlation of each variable with itself, it will be 1. I'm more interested in the off-diagonal elements. When you look at the correlation of the factor score 1 with that of 2, the correlation value is 0. Have a look at the Pearson's correlation value. It is 0, 0 again, and 0 here. And the significance value is 1. It is 1 for all the boxes. What does it indicate? It indicates that the new components that we have derived in the data are uncorrelated. Let me take you back to the original correlation matrix. This is with the 21 variables. We saw that the correlation was on the higher side. There are a lot of variables which have a high correlation. In fact, it exceeds 0.7 in many cases. So after performing PCA, we are getting new components which are completely uncorrelated. Now you may ask me, what is the benefit of this? The benefit is that if you're doing any advanced analysis, we can use these components as the independent variables, because these components respect the assumptions of linear regression. One of the important assumptions of linear regression is that there should not be any multicollinearity problem, or in other words, the independent variable should be completely uncorrelated, which is what I have. The input variables or the input components are completely uncorrelated. Now, before I end, I'd like to address a couple of questions. People often ask me, is PCA and factor analysis one and the same? I have used these words interchangeably. However, there is a difference between PCA and factor analysis. You may ask me, what is the difference? PCA and factor analysis, both these techniques reduce dimensionality. However, PCA focuses on explaining variance and identifying patterns. Factor analysis, on the other hand, focuses on identifying underlying factors and latent structures. Now, what are some of the common applications of PCA? PCA is used for data visualization and exploration. PCA is useful for feature extraction and dimensionality reduction. PCA is useful for noise reduction and data cleaning. Lastly, PCA can be used for clustering and classification. So this is about today's video. We have seen how we can run PCA or principal component analysis on Likert scale data. I hope you have found this video useful. Do let me know in the comment section if you have any questions or you need any further clarification. Thank you so much for watching this particular video. Have a great day ahead.